We're going to look at the robot arm. This is a 2-link robot arm. It's an example of inverse control. This will be a project after the one we're currently working on, which is the rotary arm. I call this the 2-link robot arm. And of the architectures we talked about, this is an example of inverse control. Did we start this last time? I mentioned it, that's right, right? Yeah, okay. So there's a base for the robot arm. Put some axis on it. So there's the height each. Their link arm will go down like this. Track the position here. X1, Y1. Position here. To Y. Angle is θ1. This angle, this joint angle is θ2, and it's controlled by motors joint. So you can set that motor at this angle, same with that one. So let's go over here and draw just kind of a stick figure. Because what we're going to do is develop equations for x1 and y1, x2 and y2 as a function of θ1 and θ2. So we're really going to do a math model of the robot. So that will be our robot instead of actually physically having it sitting here in the room. So this is the height h. And this goes over like that. Draw a right triangle. Like that. This comes down like that. Draw a right triangle here. This length is L2, this length is L1. I didn't label this over here, so let's do that. So this thing is θ1. So this is θ1 minus 90 degrees. Figure out what this is. I'm going to call it just theta. We can figure out what it is relative to θ1 because of the sum of the angles of the triangle at 180. So that gives us the formula. So what we've got 90 plus θ1 minus 90 plus theta, which is what we're trying to solve. So the 90s cancel out, and we solve theta, and theta turns out to be 180 minus θ1. So that gives us that angle, and we're going to do sines and cosines to get the length. And then the other one we want is this angle here. And that's going to be theta 2, which is this whole deal, minus theta. And so then we can calculate the length of this side and the length of this side, and that's going to be our x distance out. We can calculate the length of that, and then the distance down to here, and we can calculate the vertical locations of those just based on the. So x1 and y1, which are this deal here in this spot, x1 is going to be L1 cosine theta 1 minus 80 degrees, right? Let's just trade on that angle there. And then I will do y1 will be h plus L1 sine of x, and then this is h plus this extra distance here, which is the sine. All right, and then we're going to do x2, y2. So x2 is x1. Got that. And then I need to add on this extra part. So it's going to be L2 sine of this thing here. So after you substitute in for theta, theta 2 minus that thing, then you get that whole deal there. I guess that's easy. You just flip the sign, and that's what I put in there. And then y2 is going to be y1 minus L2 cosine. That's the thing. And this is what we really want here. This tells us the position of this indictor as a function of these two angles, theta 1 and theta 2, that we can set on the middle. So in fact, that's the block diagram of the robot. Draw it up here. Here's our 2D link robot. Theta 1 and theta 2 are the inputs. And I go over these formulas, and out comes x1 and x2. So that's the system. What does it mean to do inverse control? It means that we want to invert that. We want to say, I want to put the indictor at a location, say 10, 5. If I put that into the controller, the controller is going to figure out the thetas that are needed to put the end effector in the spot that I want.
You mean x2, y2 there?
Probably. Yeah, what am I doing? There we go. Thanks. And so, can I erase this right here? So you guys caught up? Everybody? Good?
Can I take a photo?
Sorry, what?
Can I take a photo? There was a lot of traffic. I just got here.
Wow, traffic?
Yeah, on 135. It took me 42 minutes to get here, and it's a 20-minute drive.
Yeah, I know when I was coming in, there was a wreck at 21st and 135 this morning. Fortunately, I didn't even get close to that. I can give you a minute if you want to catch up.
No, I'll just take a photo.
Okay.
Thank you.
Yeah, you good?
Yeah.
You can keep writing. I'm just going to erase this little part right here. Because I want to draw a controller attached to that thing. to specify a desired value. This is what we want. You can call it desired or a reference. Let's call it a reference. That's probably more technical. So we put in where we want the end effector to be. The controller is going to figure out what the thetas need to be so that when you put those thetas in, the robot goes to the spot we want. And that is inverse control. Now, when you do the project, and I'll mention this when we finally get there, you can actually take these equations and you can invert them. Called inverse kinematics. If you do some operations on this, I don't remember how it works. You square stuff and add sine squares and cosines. But anyway, you can solve this. But I don't want you to do that because the point of the equations is not to just equation solve it, it's to show the technique of inverse control. And maybe the model here is not 100% accurate. In other words, maybe the lengths you don't know exactly. And so we want this thing to learn to give us the values that the robot's actually given. So the equations, don't do that. The equations are like our robot simulator. And we imagine it being a robot sitting in the room, and we put the end effector at a certain, we set the values of theta at different values, and then we record where the end is, and that's how we get data. So think of this as this black box like this. It just happens that we know the equations that go in there. So how do we train this? The strategy of inverse control is you put a bunch of different thetas in, and you record where the end shows up. You take the robot, and you put in a bunch of thetas, so you vary this angle, vary that angle, record values here, and then we'd end up with a data set with all those thetas that go in, and then where the end came to be. So we collect the system data by varying. This is key. We got to vary theta 1, theta 2. Which means we got to figure out how to vary these thetas to cover the range of motions we want to go over. For this, it's fairly easy to look at it and do that. But for a general system, this may be harder to do, because you don't know what inputs lead to what outputs if you don't know the system itself. So we vary those, and then you end up with a set of data where here's my, I don't know why arrows go up here. You input some theta values, and then you get x2, y2 values collected from the robot. So you have data. And those form pairs of data, but that's forward pairs. But then for inverse control, you just flip. So this is the training data. And so all you do is invert. So this is the forward system data. We invert it to get training data, so that's all I really do. If you're doing this in Excel, you simply use the equations over there. You put the thetas into the equations. You make this cell that calculates x1, this cell that calculates x2, and then you copy the cells over and invert the data, and then you spit it out into an ASCII file, and you've got your training data. So you're going to have y, sorry, x. Y2, theta 1, theta 2. You don't have to do any rearranging or anything. All you do is flip the column. And there's your training data. So that's how you do inverse control, and it's a nice, easy example because we can visualize it. It's not like a chemical system where we can't see the chemicals doing their thing. In your head, you can see this robot doing its thing, right? In fact, your body contains one of these. Here's the base. Here's the first link. Here's the second link, right? Like that, in 2 dimensions. So, just as a thought experiment, let's say with our base, and I set this angle like 40, let's see, it's going to be all the way up to here, so this angle is going to be 45 plus 90, so 135, right? We put it out there. And then let's say I set this angle at exactly 90 up here, and that puts my link out here. So far, so good, right? But then what if I set this link at 45 here, and I set this at, I don't even know what that's going to be. Probably 180. No, it's more than that. 180 plus 90, what's that? 270. 270? 270, right? Not 370.
Yeah, 270.
And none of that would get us at the same spot. Well, let's just say this is it's like we're over 2 and 1, so let's just say that's 2, 1, just for the sake of argument. So what that means is that if we just look at these 2 sets of data, we put in 135 and 90, and we ended up at 2, 1. And then we put in 45. 270, and we ended up at 2, 1. That's legit. Look at it. It works, right? There's nothing wrong with that data. But let's invert it to train now. So invert to train. And what do we have? We've got x2, y2, theta 1. Theta 2, it's like a 2, 1. And the target answer is this. I got 2, 1, and the target answer is that. That's a problem, isn't it? Because we're saying, okay, I'm going to tell you 2, 1, and I'm going to say the correct answer is 135.90, but then I'm going to tell you 2, 1, and I'm going to say, oh no, the correct answer now is 45.27. That means that the inverse does not exist. In mathematical terms, it's not 1 to 1. In other words, each unique input doesn't have a unique output and vice versa. So can we fix this? Otherwise we're dead, right? I've just shown you an example where if we vary theta like all up and down, and we vary that one all up and down, that we're going to get duplicates that don't match. So can we fix it?
Restrict the domain, can't we?
Yeah, we can restrict the domain, which is how you take a function that's non-invertible. And in fact, what would we do? We could simply say, okay, this angle has to be less than 180 or something like that, right? So we take away this duplicate. It's called a kinematic inversion to get you to the same spot. So we could restrict the domain and just leave out this training thing. In fact, we could go through the whole training set and knock out all the duplicates, and it would be good. So that will be the next project that comes on. Your robot arm, the single link rotary robot arm system model, that's not a controller, it's just a system model, is due next Monday, right? Yes, started on that maybe over the weekend? No, because you've been doing design, right? Yeah. Again, don't wait till Sunday night to do it.
Okay. I have a quick question on the
Just like you don't wait till the night before you're flying out to notice your driver's license expired, right? Yeah, sorry, yeah.
So on the little input function we had our like torque, beta, omega, and on the output, you had x1, t plus 1, right? Since our steps of t are 0.1, should it be t plus 0.1? Or
Oh, did I write it? That's, in fact, we'll get into that. There's all kinds of shorthand notation for time steps. And I apologize, I probably jumped back and forth with the notations there. So what it really should be is x plus, sorry, x is t equals delta t. But often this is shorthand notation, the time steps are right at equals of like your time step there is 0.1. So typically you might write this as x k times 0.1 times the time step. And then k is just counting how many time steps you're at. Or you might even shorthand write this as just x subscript k. And then if you know what your time step is, sometimes in discrete time systems, they'll just write this. And that just says you go forward one time step. And I know it's confusing. So to fit with what I've been showing you before, this is what I meant. I apologize. Everybody get that? Yeah, because when we were doing the system modeling, we were just assuming a time step of 1 because it made it easier rather than writing 0.1 or 0.005 or whatever the time step is. Any other questions on that? Should be real straightforward. I've given you the equations and told you exactly what to do to generate the data. So this is a project so that you get your feet wet in generating data, getting the data set out right in the right ASCII format so that NeuralWorks takes it in, and then you can play around with training. Yeah, well, it's obviously it's also a good example of system modeling, like we did.
Could we also just, would it take 2 different neural nets, or then it might just be other methods, but do both cases of the domain restrict it in either direction? So like make sure theta is greater than, theta 2 is greater than 180 degrees as opposed to being less.
Yeah, there's no reason why you couldn't have a separate network for each domain. You'd have to have some kind of strategy to figure out, well, which one you're going to use in what situation. Yeah, because maybe you're moving from one position to another position and there's something blocking that, so you might actually want to drive the robot to the other inversion. All right, I need to remember to upload a paper for you guys to look at on Blackboard. The next example, and I think we'll get started on this and then we'll have to finish it next time, is a tractor trailer truck. That wasn't what caused your traffic jam, was it?
No, there was like construction on the side, so then only 2 lanes were open and people were just driving like 5 miles an hour.
Yeah, crazy. We had a visitor from NASA Ames. You guys know where that is? It's in Silicon Valley, just up the highway towards San Francisco. So he lives out there, and there's traffic out there is crazy. He got here, and He stayed out near, you know, where Chicken and Pickle is, right? The Warren Theater. He's at one of those hotels. He had a meeting here with us at 9:30 and he showed up at 8:45. He apologized and he said, well, I had no idea how long it would take me to drive the 5 miles to get here. Because out there, it could take an hour and a half. You know. That's pretty funny. And then we took him, jumped in the car here and drove him all the way out to Textron on the other side of town. The tour there. And we got there in 20 minutes and he was just totally impressed. And then we went to Carrabba's to eat and we got there and put our name in and 5 minutes later they called us to sit down and eat and he was triply impressed that we could get into a restaurant that fast. In fact, the next time he came here, he said if he could talk his wife into moving here, he would when he retired. All right, so this all was started by the traffic and the truck factor effort. So this is an example of how to train a neural net to back a tractor trailer truck up to a loading dock. Anybody in here good at that, backing trailers? I'm not. I'd be lined up with the driveway, trying to back straight down the driveway, and I back about 20 feet, and I have to pull forward and get straight down. Some people are good. I have a friend who can sit there and back a boat up, pull past the parking spot, just back the boat right into the spot first time. So this is not an easy problem, and I'll show you the equations of the truck so you can see how nonlinear it is. Well, this thing is called truck backer upper. Kind of a cool name, isn't it? The PhD thesis by a long time ago, like in 1987, I think, by a guy named Derek. And his advisor was Bernard Widrow, which was one of like 3 or 4 people that were really doing a lot in neural nets before it caught on and became really popular. And I'll upload the Blackboard paper. This is a highly nonlinear system. And it's a tractor trailer. Which is the truck cab and a trailer. And a good friend of mine in college, his dad drove trucks for a living, long haul trucker. And he said, there's no such thing as a semi. That these big 18-wheelers are not called semis. I think what he was saying is that some of the trucks where the cab is attached to the truck itself, or the ones with the really short tractors are called semis, but even those, he said, those aren't semis, it's always called a tractor trailer. For whatever that's worth, I just thought I'd mention it. So here's a picture of the system. Look on the chat. Anybody has said anything? I've said dash, 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 dash. That's because the cable is pushing it. Sorry, I'm erasing the dashes. I think we're good. So here's the loading dock. And the location of the loading dock is XDYD. And in fact, in the paper, he sets this to be the origin of the problem. Everybody in here seen a loading dock? it's kind of a raised thing about this high, so we can back the truck up to it, and the bed of the truck matches the dock, and you can offload stuff with forklifts and all other stuff. If you haven't seen one, the Dillons at Central and Rock, you go around behind it and there's a loading dock there. There's more around, but that's one. There's the dock. And so out here sits our truck. There's the trailer. It's got wheels. I'm not going to draw all 18 wheels. And it's attached to a cab or the tractor. In this paper, he calls it a cab. And it has wheels and it steers, the only steering are the wheels up here. So the control input is a wheel angle that I'm going to call W. And then we're going to track the state of the tractor and the trailer with an XY location of the rear end of the trailer, the midpoint of that. And then this is cab location. And then we know this angle is called theta of the trailer. And we know that angle is called theta of the cab. And in the equations, we know various lengths. Let's see what they're called. So the length of the cab is DC. And guess what the length of the trailer is? DT. And so this problem is set up so that it backs at a constant speed. So we're not trying to control the speed, it's just kind of an idle backing up. And the neural net is the artificial driver, and it's going to control the wheel angles as a function of time, so that no matter where the truck and trailer start out, it eventually backs its way up to the dock. And so the goal is to get the trailer backed up with that endpoint right at the dock, and theta of the trailer equals to 0. So I'm going to formally make that statement. First, we want to define the state vector. This is really just a list of the variables that describe the truck position. So the state variables that give us the truck position, or really the truck state, are just the ones we've listed there. Cab stuff, trailer stuff. That's it. And this collection is a vector of values, so we call it the state vector. And in this paper, he calls it S. Not very imaginative. And then W is the input of the system. It's the front wheel angle. So here's the shorthand notation that I started to talk about. All of these are a function of time. And so in the paper, you will say, well, the state vector at time step k, that is time t, t is equal to t1, t2, all the way to the final time at time steps, whatever the time step is that we choose, delta t. So T1, T2 is T1 plus delta t. Whatever delta t is. And so he'll shortcut the notation S at time step k. They'll just subscript k here to avoid writing parentheses on that. And in fact, that you can write that as k delta t, right? Because it's just k time steps times whatever delta t is forward. So the problem is dot is at 0, 0. Truck is sitting out there at some state S subscript 0. So that's at the 0th initial condition time step. Truck moves backward at a constant speed. And we want to find the wheel angles at time steps k from the initial position up till some final time. And we'll talk about how we decide what that final time is. How long do we back up the truck and what that means. So we want to find all of these values of the wheel angle at various time steps so that the truck ends up at the top. So the truck system is really, that's all there is to it. It's at its current position. And the truck backs up one time step at a wheel angle that's given, and it ends up at a new position. And that's all the equations in which we give. So this is a position at time t, then it backs up, and maybe it ends up at a different angle, at a different position, and the cab's at a different spot. You get the idea, right? So these equations tell us the truck's here, it backs up one time step, and now it's here. So there's the equations. Yeah, but if you go over there, I'm going to list the constants here. R is the distance, front tires, new one time step. So that's how they're controlling the constant speed. D sub C we already defined. That's the cab, that's the truck. So I'll list it again. This is the length of the trailer. And then we pre-calculate these collections of terms called A, B, and C. So these are defined to be our cosine of the wheel angle at the current time, the cosine of the cab angle minus the trailer angle at time step k. So I guess I should list this. So now we're saying we're at time k, and we're going to calculate being at time step k plus 1. Right, so we're at time step k, we stick in the wheel angle that whatever speed level we do, calculate A goes in here, Then we put in the current location angles of the truck. And we calculate this more. So we get the new trailer position, at K plus 1, from the current trailer position of K. And the truck angle. And this is just trig on the trailer. Yeah, R1 in here, so this is the distance that the thing moves in one time. And then we have to update the cab, so this is what the trailer does. And we get new angles for both the cab and the trailer. First tangent. The there's the real angles going here. And I got another formula, big thing down here. Then we update the cab location. Time step. I got everything. I didn't write this on the board to torture you. Hopefully it's not completely torturing you. And to make your hand tired, I didn't do that. The point is, as you're writing this down, you believe this is a nonlinear system. Like linear, it would be states multiplied by numbers equals new states, right? Whereas here we've got, at the very least, we got sines and cosines going on over here, which is nonlinear. On top of that, we got more sines and cosines here, more sines and cosines divided by other sines and cosines, and then top it all off, we got the inverse tangent. So just looking at that, it's obvious that it's a difficult nonlinear control point. So I haven't drawn a block diagram, but essentially what this is, a block, is here's the truck equations. And it takes in the current state and the wheel angle. You can see that, right? The wheel angle goes into the formulas with all of the x's and thetas of the cab at the current time step k go in. And what we get out is the state at the next time step. So the first thing we're going to do is model the truck with the neural net. Easy. We just write down a neural net. Once we draw that block diagram, we replace what's inside with the neural network rather than the equations, and then we have a system model. So here's the artificial neural net. I'll show you in a minute why we need a model, and then I think we'll be done for the day. Here's the truck model with the neural net, and it needs input for each value that we're sending in. As I can see which one I need to list first. So 1, 2, 3, 4, 5, 6, 7. And then this is the state vector. There's all the values at current time step, so that is the state vector at k. There is the control input. The 45 sigmoid neurons in one in layer. And then out comes the new state. Now you draw a bunch of connections here. So this is the state vector. And so now you have everything you need to know. Oh, these are sigmoid as well. You could create this neural network inside Neuralink. All you would need to train it is data collected from the actual truck. In other words, drive the truck around. And keyword backward, because that's what we're doing. How would you learn to drive a truck around backwards? Pick a big parking lot with no light poles, right, and no other cars, and start backing it up and turning the wheel and seeing what happens. So that's what we do here. We start out at different positions in the parking lot. We just do some wheel angles as the truck backs up, collect the data, where it ends up at the next time step, keep doing that. And that exactly is the training data that goes into the network. You don't have to do anything with it. Just collect time step data as you back the truck up. That's exactly what he did in the paper, is he just backed the truck up a lot. collected the data and trained the system model.
Would this model only work for like an individual velocity or an individual speed?
Yeah, because it's all that R is the distance, and so it's a constant speed. So you could add to this, you could put a throttle command on the truck, right? So I guess we can just key, right? But he doesn't do that. He tried to keep it simple. So he said the truck is pretty much just backing up at constant speed.
Would it work with a truck that's like a different length than for its cab or for the trailer?
Yeah, you'd have to retrain it. Because, yeah, because those lengths went in here, right? Yeah, the DC and the DT. So if you change trucks, you have to retrain the system model. So you drive the truck around backward, and you collect the data. Let's show you just an example set of data that you're going to get. So we have the truck at time step K, the wheel angle at K, and then we're going to get the new value of K plus 1. And so if we start out at an initial position, S0, and the angle's at a certain angle, then we're going to end up one time step ahead and collect that data. And then that becomes our new position, new wheel angle, end up at a new position. That becomes our current position. Then we end up at a new position, and you keep doing this for a while, and then you go back and you reset the truck at another new initial position, and you just keep collecting the data, and you train. All right, I want to show you the controller, and then we're going to stop there because the training actually will take about a half an hour or more. And if you draw this big picture all the way across the board, it's kind of cool how it works, but it'll take some time. All right, so we want to control this thing. This is the truck. And what we want to do is put a controller on here that looks pretty simple. It's just going to spit out the wheel angle, and it's going to look at the current state. Because that's what the controller is going to do. It says, okay, even as a human, you'd say, I'm here, I'm looking backward through my rearview mirror, I want to go backward, eventually end up at the dock, and so I'm going to figure out what wheel angle I'm going to do currently to go back one time step. That's it. This is the controller. And it's an artificial neural net. I'll show you it in a minute. But then the model, the neural net model goes down here in parallel with the truck. Because it does exactly the same thing that the truck does. It takes the current state and figures out, well, what happens to the truck. We'll put a hat on here because it may not exactly match the actual value. Remember, this is a neural net, and this is a neural net, so I guess I should put A in an artificial neural net. So the model is used in the controller to train the controller, and this fits the architecture that we call neural model adaptive control. So that was one of the architectures that I talked to you about. So this is an example of that, where we have a controller and a model that's a neural net, and we're going to use both. And here's what the neural net looks like, and that's going to be a decent stopping point. We'll get out of here a little early. If you have some extra time waiting for your next class, you can start working on the robot arm project. So this thing is going to take the current state. 2, 4, 6. X, C, A, I, C, K, A, C, K. Trailer, same deal. This is where I'm sitting at. And I'm going to calculate what I'm going to do next. That's the wheel angle that then is going to go through the truck, and then the truck's going to back up with that wheel angle to the next time step. He did 25 sigmoid here. He was early on in this kind of stuff. I don't think he optimized his network real well, but it works really well. And so I think he probably had a lot more neurons and then narrowed down to try to get as few as he could. And then this is the same thing. We're going to train the controller by backing the truck around as well, backwards. But we've got to figure out, well, what error do we calculate to train? And how do we train the controller? Now, if we're training the model, we use the data from the model. So all we're doing is saying, well, right here's the neural net answer. Here's what we really should have gotten. So this is the model error. That's real obvious, right? We put the same inputs into the actual truck as we did the model. And so if the model were perfect, it would put out the exact same state. But this would be the error that we'd use to backprop through the model to train the model. But next time I'll show you, well, how do we train this thing? And it involves backpropagating through the model, but we have to do it in a special way. So that's where we'll start next. It's quite amazing how well this works. I'll make sure I get the thing closer to the blackboard so you can take a look. I did the first two. That's the first two.